Next, we have a talk on AI for fusion by Dr. Tamara Norman. Tamara is the fusion technology lead at Google DeepMind. Her team applies AI to accelerate the path towards energy fusion. Her work spans simulation tools, including the open source TORAX and large-scale research infrastructure. Previously, she works on training large-scale AI models in TORAX, specifically on model partitioning and user-facing APIs. Thank you.
Hi, so today I'm here to talk to you about AI for fusion. Some of you might be asking, why am I here talking to you about fusion? Fusion's a really interesting problem that's been kind of around and people have been interested in it for a long time. So how can you replicate the fusion that happens on the sun, the fusing of hydrogen and hydrogen to create energy that's kind of responsible for all of the energy we have on Earth indirectly? How can you kind of replicate that on Earth? In order to kind of generate carbon neutral energy. So as many people are aware, or everyone's aware, even though people are putting in a lot of effort to kind of stop the rising of CO2 levels, they're still definitely rising today. And fusion kind of is this option of having a really clean energy source that's also really, really fuel efficient. So just 1 teaspoon of fuel for fusion is the equivalent of a tanker of oil for the same amount of energy that you get out. But why now? Why fusion? So fusion's kind of been in the research space, and it's kind of been one of these problems that's always like 20 years away, always 30 years away, and never feels like it's getting closer. But recent advances that I'm going to kind of talk to you about now mean that fusion feels like it's coming much sooner. And actually, CFS, who are a kind of startup based in the US, are trying to design a reactor that will achieve Q greater than 1 in 2027. But what might you ask is Q greater than 1? So Q is just the ratio of power out to power in. Q greater than 1 is called scientific break even. This is when kind of we get more energy out of the fusion reaction than we put into it. And then the next milestone is Q greater than 10. And this is called like engineering break even. This is kind of the level that's needed to show that kind of fusion can be used as like an actual commercial reactor, like an actual source of energy. And it's what kind of people are aiming for. So there are a few other terms that might come up, one of which is triple product. So when people talk about fusion, there are actually many different technologies that people are trying to achieve fusion on Earth, which I'll go into in a sec. But when you talk about these, you're trying to kind of maximize the triple product that you create. So you're trying to maximize kind of the product of both the plasma density, the plasma temperature, and the confinement time. And when you kind of maximize all of these and reach a specific level, so 5 times 10 to the 21 is necessary for Q greater than 1, it means that the kind of fusion reaction is self-sustaining. It means that the kind of particles are kept towards a high enough temperature for the reactions to occur without any external heating. And if the reaction's occurring without any external heating, it means that you're generating energy without needing to put loads in. And then this just shows kind of what happens. So in the sun, they typically do hydrogen-hydrogen fusion. But here on Earth, we're actually more interested in what's called heavy hydrogen. So this is the reaction of deuterium. So instead of just a proton, it's a proton and a neutron. With tritium, which is where you have 2 neutrons. And the reason for this is that you basically can generate much more energy at lower temperatures, which is much more reasonable to expect on the Earth. And one other cool thing about this is I talked to you before about kind of it being really fuel efficient. It's also really fuel abundant. So deuterium naturally occurs kind of in the sea. It's kind of everywhere. And then you can get tritium using lithium to kind of breed tritium. And that's how you kind of can generate this fuel on Earth. But why aren't we doing it today? There are still kind of significant kind of scientific and engineering challenges that needed to overcome in order to kind of successfully achieve these Q greater than 1 and Q greater than 10 milestones and turn this into kind of a commercial technology. But one thing that's always also interesting is that there are many different technologies in the race. And these technologies also take advantage of kind of different properties of the triple product. So the first two are magnetic confinement fusion. And here, they kind of maximize like all of the things, whereas lasers, yeah, they much more maximize the density and the temperature, with the reaction being almost instantaneous, so the confinement time being really small. So the first one is tokamaks. These are probably the most common type of technology. And they basically use axisymmetric magnets that wrap around the edge through the middle to create a plasma which has an induced current in it. This means that kind of the plasma itself has current flowing through it due to the induced voltage. One thing that when I got into the fusion world that it really reminded me is that back at school when we learned about like Fleming's left-hand, right-hand rule, is that the same technologies apply here. So in fusion, we're kind of pumping a voltage through the coils, creating a current which creates the magnetic field, which keeps the plasma away from the wall. And then because that's the charged particles throwing through a magnetic field, that creates an induced current and an induced voltage. So yeah, magnetic confinement fusion. There are a few different tokamaks I've got featured here. JET, so the Joint European Tokamak that operated in Oxford, but is now decommissioned, holds the record for the power over 5 seconds. And then WEST, which is in France, holds the record for the longest plasma, so 22 minutes. So combined with that, you can kind of hold plasma fusion reactions for a long time. Stellarators, you can kind of see here, it's kind of a bit of a like twisted donut. So here they kind of twist the reactor and have twisted coils such that the plasma can kind of flow continuously, assuming that you can kind of dissipate the heat as needed. And this holds the triple product record for the longest plasma durations. One thing that's interesting about stellarators is that with tokamaks, they're relatively simple to model. So with tokamaks, they're axis-symmetric, so a lot of the calculations can be done on this 2D grid or even like a 1D grid. But with stellarators, because of this twisted nature, a lot more of the reactions have, a lot more of the simulations and calculations have to be done in 3D the whole time, which previously, for a while, made them kind of computationally and really hard to kind of study and do things about. But advances in technology and AI and things like that have made it much more kind of, there've been a lot more work recently in kind of using AI to start to design stellarators and really accelerate that. And then the third one is lasers. So NIV is actually one of the only place, or the only place where they've kind of achieved Q greater than 1. They hold a record for Q of 4.13. But this only produced 8.6 millijoules of energy, and they can only actually run a few pulses a day. So although they've achieved the largest records, there are significant advances in kind of technology that would need to happen in order to have this happen continuously. And there's also a really big difference in lasers between Q plasma and Q engineering. So here they're firing basically massive lasers at like a tiny pellet of fuel, and there's a really big difference between kind of the fusion calculations and numbers that are achieved versus like what's actually achieved in practice. So why now? I kind of mentioned it at the start, but one of the really big things that's happened in the kind of fusion industry recently is actually due to like advances in materials that can happen. So CFS, who are one of the big players in kind of this startup race, have developed these high temperature superconducting magnets. And one of the really cool things about this is that it essentially means you can kind of have magnets that can hold much higher, with much higher currents that are much smaller. And this enables for designing much smaller fusion reactors, which are much cheaper to construct and much easier to construct and manage. And then the other thing, which is really interesting, is as well as kind of massive increases in the amount of government funding in this areas, there's also actually been a massive increase in the number of startups in this area. So it's gone from like basically none to over 50 startups in this area, which seems as though it's kind of a really expensive, it's really expensive to build a fusion reactor. This is a really good sign for kind of that it's becoming much more commercial and much more likely to happen. But what about the problems? Where can AI really help, and why isn't this all already happening? So one of the key interesting areas where AI might have a really big impact on fusion is robotics. The thing with the deuterium-tritium reaction that we saw earlier is that it does produce neutrons. So it is radioactive. It's nowhere near as radioactive as fission, but it is radioactive, and you can't just kind of send a human in to repair something if something goes wrong. So there's a lot of stuff in robotics for maintenance, for monitoring, and actually there's some really cool haptic feedback robots that have already been used at JET in Oxford. The next one is materials. I mentioned the high temperature superconductors earlier that have enabled kind of key advancements, but also the inside of a fusion reactor is a pretty horrible place to be. You've got neutrons, massively high temperatures, so finding materials that can kind of handle this is something that will continue to have a difference in fusion. And then tritium. So while deuterium is very abundant, tritium is not very abundant. It's easily produced with lithium. There's loads of lithium in the world, but it's still quite hard to make. Tritium actually costs between $30,000 and $40,000 a gram. So it's one of the most expensive materials in the world. Just because it's so kind of rare and hard to produce, you basically have to produce it using kind of in these kind of fusion spaces. And so one area where there's a lot of work being done is kind of making this reaction self-sustaining. So can you actually use the neutrons that are being produced to combine with lithium to produce this tritium kind of within the same cycle of the fusion reactor? Can you make sure that you can kind of recover it and actually regenerate it for kind of future reactions and future reactors? And then these are ones that are much closer to some of the work that I've been doing and I do at DeepMind, is the idea of digital twins, and digital twins veering into the idea of a world model of a fusion reactor. As you may have been able to guess, it's quite expensive to build a fusion reactor. It's also then quite hard to kind of test things on it. And so having really good simulation, really accurate, fast simulation can make a key difference to being able to kind of test out new ideas, see what will happen. You don't necessarily want to build a massive fusion reactor and then find out that some of the assumptions you made were completely wrong. Another area that's kind of very clearly been accelerated by machine learning, and actually one of the areas where kind of neural networks are kind of very prevalent is in surrogate modeling. Fusion's kind of made up of a massive number of the fusion world has a massive number of kind of simulating tools, some of which, or many of which, are quite old, written in things like Fortran, lots of things in MATLAB, these kind of things, and they're also often quite expensive to run. It can take days or weeks in order to do kind of a full simulation. Surrogate models enable us to kind of collect a suite of data, run the model, the expensive model to collect a suite of data, and then create a neural network that can kind of approximate that model, which enables us to use it for kind of fast and accurate simulation, and enables us to do things like control or planning or any of these things using a really fast simulator, which enables a lot more discovery. And the final thing, which is what I'm going to go on to talk to you about next, is actually tokamak control. So leveraging these improvements in simulation, we can help develop plasma pulses and also develop robust controllers for plasma simulations. So yeah, now I'm going to talk to you about some work on the magnetic control of tokamak plasmas through deep reinforcement learning. So this was work done at DeepMind back in 2022, which was actually just before I kind of joined the project, but we've been kind of continuing to push various avenues of it now, but I'll go into a few details about what we've been trying to do here. So this is kind of the inside of a tokamak. You can see the coils, so the yellow coils, the red coils, and the kind of blue coil as well. And then you can see the plasma inside. So basically, this is TCV, which is a tokamak in EPFL, so in Lausanne. And it's designed as like a research tokamak. So it's been around since the 90s, I think. And it's been used by many PhD students over the years to kind of test out ideas. And so here you have the plasma, and fusion plasmas in a tokamak are by nature unstable. This means that you continually have to kind of change the voltages in all the coils in order to keep the plasma alive and respond to the measurements you get back out. So the controller here operates at 10 kilohertz. This means that compared to a lot of the things you've been hearing about, any model that we put into the controller has to be able to run at 10 kilohertz in order to keep the plasma alive. And so designing something that was able to kind of do all that we needed to do and run at 10 kilohertz was a key part of the problem. So what are we trying to do? So within a fusion reaction, you're trying to control all of these things. You're trying to control the plasma current. You can try to control the position of it, both vertically and horizontally. And then you're also trying to control the shape. So if you can see in a lot of these, you have the sharp black line. That's called the last closed flux surface. And that's kind of the shape that you're looking to control. So what have they done since kind of the 90s? So traditionally, they had things called the PID controller. And this is where you'd basically pre-compute the kind of trajectory of voltages and currents that you want to happen in the coil. So you'd pre-compute the currents, and then you'd use that to pre-compute the voltages. And then you'd pass this in as a trace, along with some observers and some kind of a matrix, basically, which said, basically, how do I... you'd basically calculate the errors of your measurements, so how far off from where it should be is my plasma, and then can I basically adjust my voltage and coil targets in order to bring it back to where I want it to be. And so these controllers were implemented in like analog systems, and yeah, you had to basically tune them by hand though. So for each different shape, for each different trajectory, you had to retune your kind of matrices, which were used to kind of adjust the voltages. So what if we can kind of replace that? What if we can replace a lot of the kind of hand tuning and just replace that with basically a control policy that's been trained? It's really easy to kind of generate one for each new trajectory and idea you want to try out. There's kind of no different boxes. It's just a single box that you can deploy on the machine. So I'm sure you've heard this over the course of the week, but in reinforcement learning, you're basically trying to learn a sequence of actions through trial and error that achieve a high reward. And one thing that's important that is where reinforcement learning really shines here is that it's a nonlinear stochastic system. There's a lot of instabilities in a fusion reaction, and we need to be able to handle that. And then there's also that you have a high flexibility in the reward function. So this has been really useful for when adapting to kind of the sim to real nature, so adapting between what happens. But yeah, the environment that we ultimately want to run on is a TCV tokamak. As many people might have come across through robotics, through many other things, you're not really going to like train on the tokamak. There's only one. You can only run a pulse every 15 minutes, and each pulse is 2 seconds if it goes well. So instead, we trained on a simulator and then used the reward to account for kind of any differences between the simulation and reality. So what actually happened? We started by just trying to keep the plasma alive. So as you can see from the first one to the second one, the first one lasted just 0.024 seconds. So if you basically don't do very much, the plasma just dies. Versus over here, where we managed to keep it alive for 0.55 seconds. And the key things that it had to do there were basically control the vertical instability. So the biggest instability in these plasmas is that if you don't do anything, they'll either fly up and hit the top or the bottom of the plasma. And the other one is maintain the plasma current. If you don't do anything, the current in the plasma will just drop, and then it will kind of fall apart. The next thing is, once they'd done that, the next thing was actually to stabilize the plasma location. So to basically decide where you want the center of the plasma to be, and to train the agent to try and keep it in that space. One thing that's really interesting about this is that if you compare the one on the left and the one on the right here, in the one on the right, the agents actually made the plasma really, really small. And so the reason for this is that when the elongation of the plasma is reduced, when it's much, much smaller, the vertical instability just drops. So the vertical instability is much higher with much longer plasmas. And so the agent, instead of just learning to like position it and keep like the exact same shape, it's actually gone, well, it's actually really easy or much easier if I make the plasma smaller. So that's what I'm going to do. I'm going to make the plasma smaller. And that's one feature of RL, is that RL is like very well known for basically taking the shortest path to do something, to make the problem as easy as possible. And then the third bit. The third bit was shape control. So here it's, instead of being like, you can make the shape as small as possible, to be like, no, I actually want you to kind of keep the shape, thinking about the shape, the currents, and all of these kind of things. So then, yeah, we were creating an agent, the optimal policy, so to maximize the future reward that you would get. So had this agent that we could then deploy. And then to train it, we actually used something called MPO. I don't know if people have heard of this. And one key feature of MPO that was really useful here is the actor critic. So here we had a critic, which was a much bigger network that we could use during training. And then for the actor, we had a much smaller network that essentially learned from the critic. So the critic learned from the simulated data, and then the actor just learned from the critic. And this meant that we could have a critic which had kind of RNNs in it and kind of much longer, bigger blocks, but that the actor could be small enough to be deployed on CPU and run at 10 kilohertz so that we could actually use it on the real hardware. So yeah. In the deployment, one thing that you'll see is that this neural network was basically just 3 by 256. So compared to everything else you've probably heard about over the week, it's a really, really tiny network. And this is because, yeah, it needs to be on CPU, but also that the features are relatively small. So we have like 92 inputs and just 19 outputs. So a lot of stuff needed to happen in order to make it work from like simulation, like actually in reality. So a lot of the tweaking, as I said before, happened in the reward function, making sure to kind of capture those things that aren't captured in the environment. And then also to improve the simulator. One thing that we found is that doing this kind of work, you're able to like both improve the model, but also improve the simulator, which helps to then improve the model. And then we use the traditional environment variation. So here are some of the results. This is actually the view from inside the tokamak. It's not the smoothest, but yeah, you can kind of see what the plasma is doing. And the big, when it goes to the end, the kind of line you can see is actually that line, that specific dot. Here you can see kind of the plasma in that shape there. So why is RL useful here over traditional methods? So RL is really useful because we were able to do kind of all of these different shapes, including kind of new shapes. It's much easier to kind of search for what's available. In particular, I think this snowflake was kind of something that hadn't been done before. So you're able to kind of search for different things, and you can basically go, you know, I want to create this shape, leave it overnight, and then it comes back to you with a controller that you can kind of use and deploy. So yeah. And then the other thing was that we actually managed to create the first sustained droplets. So in all the previous reactions, we had just a single plasma within the machine. Here we managed to have 2 different plasmas and managed to sustain them for 20 milliseconds, which was a record on CCV. So what's happening now at GDM? I'm personally working on this kind of bigger fusion problem area now, and we're kind of focused on a few key things, one of which is we partner with CFS and are working to kind of help them solve the problems that they need in order to make Q greater than 1 a reality, and also to put energy on the grid. Their aim is to have energy on the grid in the early 2030s, which seems crazy when you think about it in terms of just like how close that is, especially when fusion's always been kind of seen as being so far away. And then the other thing is that we work on an open source simulator called TORAX, really trying to improve this kind of modeling angle. And it's actually written in JAX, which makes it kind of differentiable and also makes it really easy to combine with kind of machine learning and all the machine learning models, because they also can be written in JAX as well. So yeah, thanks for listening. Yeah, if anyone's got any questions.
So I have, thank you for the talk. Just maybe 2 quick questions. So I come from a background where I am interested in knowing scaling behavior. So in this particular domain, if you were to, from your experience, if I were to double the time of stabilizing the plasma, in terms of compute efforts, like to train these models, like are we talking about a linear, quadratic, exponential relationship? What's the scaling behavior in this case?
In terms of, so I'm not sure.
Okay.
I think that it's interesting because you develop a controller which iterates at just the current time step. Yeah. And so if you found a controller that can keep it stable at the same time, that's great. I think that one thing that's interesting in Fusion is that you're basically continually increasing within tokamaks, you're continually increasing or decreasing the voltages in the current. No, in the coils. And so at some point you basically hit kind of coil limits because you kind of can't keep going any longer. So it's a combination between energy and compute. So yeah.
Okay, so it's not just a matter of, okay, let's train it longer.
Yeah, so it's not just, and often once you reach the point where you can stabilize it, you don't necessarily need to kind of keep training it for ages.
Okay, sorry. Okay, second quick question. So you're using a simple MLP. I mean, have you thought of maybe using AutoML or any other way, of optimizing the architecture of the neural network?
Yes and no. Part of the issue is that it has to work so quickly.
Yeah.
It has to work in 10 kilohertz, and there's not much you can do in 10 kilohertz on a CPU. Lots of these transformers and all of these kind of things take much, much longer to run. So yeah.
Okay, thank you.
Hi.
Hiya.
Thank you very much for your exciting talk. My first question is, do you work only with tokamaks or other approaches to fusion also, like laser fusion or plasma jet-driven fusion?
So at DeepMind, we only work really on tokamak fusion, mainly because they're all quite different. And so we partner with CFS and we partner with EPFL, and both of them are kind of tokamak focused. But we do have kind of people using TORAX who work on, still spherical tokamaks. But yeah, it's still in that space. I know that our company is doing a lot of AI in terms of stellarator design, but that's not something I've personally worked on.
Thank you. I have another question. I have been looking into the TORAX code, and I'm surprised that it solves one-dimensional transport equations, which seems oversimplified to control the real device. So my question is, why it works? Why do you think it will work?
So because because of the axis symmetric nature, that's how you get obviously down to 2D. But then a lot of these things that are governed by TORAX are kind of consistent across flux lines. So that's why, obviously not everything can be captured, but in comparisons to kind of higher dimensionality solvers, we've seen kind of equivalent accuracy. And one thing that's really key is there's obviously trade-offs between kind of speed and accuracy, but yeah. I mean, I'm not a physicist by training, so I don't know the full details, but a lot of these kind of reduced codes still get really interesting results.
Can I ask another question?
Yeah.
Can you learn from experimental data directly without any model?
What was that?
Train a neural network on experimental data without physical model.
I think that people have started to give it a go. I think that one thing in Fusion is that a lot of the experimental data is we at DeepMind haven't necessarily had loads of access to experimental data. A lot of the experimental data is owned and held by government because that's where a lot of the tokamaks are. So that's, but I think that people are starting to think about the idea of kind of using real data a lot more in the fusion space.
Okay, thank you.
Yes.